Good morning, everyone, and welcome to our short form discussion on buckling in aluminum beverage cans. This may sound simple, but the behavior of these cans under pressure is actually quite interesting and very relevant in structural mechanics. I'm Zurain, and with me are Shada and Iquan. Let's begin with the basics. Shada, could you explain what buckling is?
Buckling is a type of structural failure that happens when something under compressive force becomes unstable. Instead of breaking apart, it suddenly bends or collapses, even if the material itself hasn't failed. It's common in thin wall structures like beverage cans because they're so slender and lightweight.
Exactly, and if you look at typical aluminum cans like the ones used for soft drinks or tea, there are different types, right? Iquan, can you talk about the structure?
Yes, generally, there are two common styles, the standard can and the slim can. The standard one is shorter and wider, while the slim can is taller and narrower. Both are made from aluminum alloy and have very thin walls, which is less than 0.1 mm. Because of their shape and size, they respond differently when compressed. What's interesting is that the slim can, even though it's taller, can resist buckling better because of its smaller diameter. The shape affects how stable it is under pressure.
That's quite surprising. I would have thought that the taller can is more likely to collapse, but it seems radius plays a bigger role.
Yes, the smaller the radius, the higher the theoretical buckling strength, assuming the material and thickness are the same. But we also have to consider imperfections. No can is perfectly smooth or symmetrical in real life, and that's why engineers use what's called a knockdown factor. It adjusts the ideal buckling load to reflect reality, things like dents, scratches, or even how the can is handled during production. This factor can greatly reduce the actual load a can withstand before buckling.
Let's talk about real-life examples. What kind of buckling failures have you both seen with these cans?
A common one is when someone accidentally steps on an empty can. It just flattens instantly. Another is during storage or transport. Empty cans stacked together can deform if there's too much pressure, especially from the side.
There is a classic case of localized buckling. Once a small fold or dimple appears, it spreads quickly and the can loses its strength. This is similar to what happens in large structures like fuel tanks or silos, where thin walls are used to save weight.
So what can be done to reduce the chances of buckling in these cans?
One solution is to slightly increase the wall thickness. Even a tiny increase can improve buckling resistance a lot. Another method is using internal pressure, as in a carbonated drinks can, which helps the can hold its shape. Also, small design changes can help. For example, adding horizontal grooves or stiffening rings around the can body can make it more rigid. Reinforcing the ends, especially the base and top, also prevents stress from concentrating in weak spots. Before we end, I would just like to conclude that buckling in aluminum cans may seem like a minor issue, but it actually involves important principles of structural mechanics. Factors like shape, size, material thickness, and even a small imperfections all play a role. By understanding this, we can design a safer, more efficient containers, not just for beverage, but for many other thin wall structures too. It is also a great reminder that engineering is everywhere, even in everyday items we take for granted. Something as simple as can combine material science, geometry, and structural behavior. And when it fails, it often reveals more than just a dent. It shows the delicate balance between strength, weight, and design. In the future, we might see even smarter can design that use recycled materials, improve shapes, or even real-time sensor to detect pressure changes. So, even in a simple soda can, there is a room for innovation and improvement.
Great suggestion. So it's not just about material, but also geometry and internal pressure. It's fascinating how much thought goes into something as simple as a can. Thank you, Shada and Iquan, for the insightful discussion, and thank you all for joining us today.